So we're going to go ahead and take a look at the pKa values for commonly encountered structural types. This is the chart that I recommend using on the examination, though I suppose since it's open book, you could use other charts. This is the one that's in your textbook. If you have a physical copy, it's at the beginning of the book, probably since I think most of you have loose leaf, one of the sheets at the beginning. It's also, I posted it on Blackboard in several spots, including the old exam section as well as the old exam material section, as well as the lecture materials as pKa chart. And what it does is the number down the center right here, the number down here, these right here are the pKa values for these structures. Now, this is a general kind of like range that they're in. It actually takes over here for certain structures where there's some variation possibility. That's represented by these R's. And these R groups can be various things. And, you know, take, for example, this molecule right here. So in this molecule right here, we've got an R1 and an R2. In some cases, it can be two methyl groups, in which case the pKa of this hydrogen, so it's always the red hydrogen in the molecule on this chart. So if you print it out in black and white, be sure to either circle them, highlight them, or just know which hydrogens is, that the chart is telling you the pKa for, or just use it digitally. Now, the pKa for this molecule when these two R groups are methyls is negative 3.8. Now, when you change that up a little, let's say instead of these being methyls, they're hydrogens, which would make it then the hydronium, then the pKa is minus 1.7 for the red hydrogen. So let's just take a look so you can see what I mean by drawing out these two scenarios, two methyls, two hydrogens, just so you're following along. Okay, so here we are with our two structures. This is the generic form that you see in the pKa table. So in the case where we had the two R's as methyls, it means there are two methyls in this spot. And as the chart indicates then, the pKa for that is, just looking it up right now on my screen, minus 3.8. And then when you identify this as what we learn in GChem is known as hydronium, that is the conjugate acid of water, where these are two hydrogens, the pKa of this, when you look at the chart, is negative 1.7. Now, what if you don't see a molecule, or you don't see an example in the chart that's exactly like yours? Take, for example, this structure right here, in which you've got two methyls on this nitrogen, and we're going to talk about this hydrogen right here for its acidity. And then you've got this, which is essentially a carbon with a hydrogen, and then a bunch of more carbons with two H's on them each, and then it just wraps around in this ring. When you look at the pKa table, you really won't see anything like it. But let's just take a look at the closest example we have. So let's zoom in here on the chart, and as we can see the molecule right here, we've got two methyl groups on a nitrogen that's positively charged with the hydrogen that we're focused on its acidity. The closest thing that we have to that is right here, a nitrogen that's positively charged with a hydrogen on it whose acidity we're interested in. And it's got three varying other spots that could be hydrogens, all hydrogens. So in other words, if it's ammonium, NH4+, it has a pKa of 9.2. And then if it's got some methyls replacing it, some ethyls, some propyl groups, not isopropyl, but the chain, it varies a little bit. Notice it goes from these two H's here being hydrogens at 9.2 to being two three-carbon chains to about 11.1. That's it's a strong change. But then when you go from methyls with a hydrogen at 10.6 into the three-carbon chain propyls at 11.1, the change is much more, a little less drastic. And so, I mean, at this point, if I were to give you a molecule like this, what you can just generally assume is it's somewhere, if you look at this, all carbons all carbons, mostly carbons with one hydrogen. They're all within this, but they're bulky. They're all within this range of like 10.6 to 11.1. I mean, you could just roughly estimate probably that the pKa of this hydrogen is, I don't know, maybe I would head towards, because it is still rather bulky, I would head towards the higher pKa, because that seems to be what bulky carbon groups are messing with the acidity. They're making it a larger pKa, the more bulky, the more additional carbons there are on this molecule. I don't know, I would lean towards that, probably like approximately 11. And at this point, there isn't really a perfect answer, because you don't have a clear structure that looks exactly like one of these in the table, but it would give you a good enough range if you're comparing it to something else to, okay, it's approximately 11 for this hydrogen. So that's pretty much how you use this chart. You just kind of look at, you try to find, this is a good test of your kind of the same skill that you use when identifying functional groups. Not that these are always themselves functional groups, although often in a way they are similar to functional groups in that they're a certain arrangement of atoms. So that's a good chance to practice that skill some more, is being able to be more comfortable with this table. Like I said, these are not necessarily themselves functional groups, but rather it's still that same skill of recognizing, oh, this has a very this generally speaking has the same structure as what I'm looking at in my molecule, that kind of skill. Okay, I hope that this was helpful in using the pKa chart, and I'll see you in class.